able to, I don't know, be on this side and interact with you guys. And please ask, stop me as many times as you like. Ask a lot of questions. That's the whole point here. And I would make a disclaimer that I'm not like, I think I'm not a like this. I wouldn't call myself expert in the field I'm talking about. I know a little bit, so there are a lot of holes in my knowledge. Hopefully, I will also learn from your questions. So, but hopefully, okay, both of us. I mean, all of us will know more by the end of the week, myself included. So let's start. So what's the topic here? Topic is mixed state entanglement. So I think Leo kind of convinced me that I should also maybe give a brief overview of pure state entanglement in many-body physics, how it's often used. Maybe not all of you have worked in this field, even in questions related to just pure states and so on. So I think it's maybe I haven't prepared anything that I will just do on the fly. Some very brief maybe overview of what kind of questions that arise in many-body physics, which where thinking in terms of entanglement has been useful. So let me try to be a bit quick. So let's first discuss, okay, entanglement of pure states. Is this too small? Okay. Okay. Generally, I'm always told that I write too large. Okay, so all right. So okay, so what are we interested in? We are generally interested in, at least in condensed matter physics, we are generally interested in universal properties of stuff, right? That's what we care about most of the time. So okay, so then here's maybe one very specific question you can ask. You are given some. So okay, first of all, what is a universal property? Okay, what is a universal property? So then you have some phase. You consider some phase diagram. You have some parameters. Let's say R1, R2, and so on. You have phase 1, phase 2, and so on. And so let me first restrict to myself. Let's say grounds some system at 0 temperature. So this R1, R2 are parameters other than temperature. So then each point here can be, if I'm in the ground state of this Hamiltonian with many parameters, each point is a eigenstate of the Hamiltonian. So within one phase of matter, there are infinite number of points, right? I define universal property as something which is shared by this infinite number of points. So all of these, pick any of these points here, calculate that so-called universal property, it should be same. So here's one example, number of Goldstone modes, for example. That's a universal property of a phase of matter. Other thing could be, for example, even the dispersion of the Goldstone mode. That could be a universal property. Talking about maybe more quantum things. If you have some gap system, which I mean you have a ground state. There's above that the excited state has a finite gap in the thermodynamic limit. Then you can ask perhaps something like Hall conductance could be a universal property of the system, which is quantized perhaps. So these are some examples. So what has been observed is that at least one perspective is entanglement is like a crank which you turn to generate universal invariants for a system. And some of these invariants have been only discovered using thinking in terms of many-body entanglement. They were not previously things, so now they are. So Okay, so that's maybe one perspective. It's a way to generate things which you call universal. So here's one example. For example, I mean, just to give one example, which you may have seen this before. If you look at some gap systems, so consider a gap ground state, but that I mean, as I mentioned, that the spectrum looks like this. Maybe there are few things there, but overall, after these few things, there's a gap which is non-zero in thermodynamic limit. If you look at so what is entanglement? Okay, I've not even defined it, but let me now define it. So you're given some state psi, and so this is the eigenstate. This is this gap ground state. You look at its density matrix. So this is the density matrix for this state. And this is one setup. I mean, there can be many things you can do, but this is like a very canonical setup. You divide the whole system into two regions. Let's say spatial bipartition, A and B. So whenever we discuss entanglement, in principle, you can do many. You can ask about, in general, entanglement between many different parties. Like you can divide the Hilbert space into more than one regions. So that's called multipartite entanglement. That's a much harder topic to discuss. So most of the time, we'll be focusing in these lectures on what I will call bipartite entanglement. So bipartite means that just this, they're just two total system is a union of two subsystems. There'll be times when I will divide into three, but then again, but the third thing will be like a bath for the other two, and eventually you'll be interested in bipartite entanglement between the two of them. So I will also write, so there's a Hilbert space I will denote often as A tensor B. On that note, remind me of, so I posted my notes online. They are not, I would say, fully complete. I'm still kind of making some changes, but they have several problems. If you have seen, like, please attempt them. I have maybe at least 9 or 10 problems overall. So please try to attempt as many as possible. Ask me if you are stuck. So this notation means that Hilbert space is a tensor product over A times B. And there are sometimes subtleties with gauge theories and so on, but okay, we won't get into it right now. So so coming back to what is and how to define entanglement, you have some state, you define density matrix, then you define a reduced density matrix over region A, let's say, or you can do over B. So this TRB means trace over B. So I'm tracing out degrees of freedom in region B, which means you choose some basis of region B. You can call, for example, basis to be, for example, phi B. So this is same as so now I have a reduced density matrix. So what is true is that to characterize correlations between A and B, one very useful quantity is this thing called von Neumann entanglement, which is S of A is minus trace rho A log rho A. This is what most people, when they think about entanglement, this is what that comes to their mind. Some expression like this. This is like a quantum version of Shannon entropy, and so you can ask, how does this, for example, scale with system size? And that dependence encodes this universal invariance, which I earlier mentioned. For example, if you have topologically ordered system, then so something which has topological order, by which we mean perhaps that they are degenerate ground states, which encode some topological qubit, and they have, ground states which are locally identical. There's some global difference between them. And in that case, okay, maybe I should, let me just write down some examples of universal. So this is still like, I think this is not what I intend to talk in most of the lectures, more about mixed state, but I think probably good to see once, obtained from SA, let's say LA. This is dependence of SA on subsystem size LA. So for example, when you have topologically ordered phase, then SA looks like LA minus gamma plus some. If you have, let's say, a smooth bipartition, so this is so this is gamma is called topological entanglement entropy. Topological entanglement entropy, and this is a universal number for that phase of matter. So wherever you go in the phase diagram, it will be universal. Obviously, there are some subtleties with it, and I don't want to get into them. Sometimes there could be some spurious contributions to this, but most of the time, don't, at least when you're starting to learn about this, maybe it's first good to look at where those subtle things don't occur. So okay, so then, and then you can talk about, for example, conformal field theories. For example, in 1 plus 1D, SA is like C log L up to some coefficient here, which is universal, maybe C over 3 or something. So C is a central charge. And so, so both of these numbers, gamma and C, are not really new. As I earlier mentioned, entanglement is a way to generate new things, which we did not knew about before, right? That's a cool part. So C, obviously, people knew about C from 1980s, and gamma can be written in terms of so-called quantum dimensions of anyons. So again, it's really not new, but it's still universal. It's still useful. But so here's one interesting thing. If you go to 2 plus 1D CFTs, then SA, for example, so it will look like, again, some LA minus, let me call it F. And in this case, because it's a gapless system, the shape matters of the region. So it's a shape dependent universal constant so if you have some region like this, it will have one number. Some region like this, it will have a different number. So you may say, okay, that doesn't sound universal, but it's still universal in the sense that if you scale it up, if you don't change the shape, it doesn't change. So if you look at SA for a circle, specifically for a circle, this is what is called F. And this was no one had thought of this, or no one knew about how to express this in any other way, in any simple way. And this turns out to be extremely useful universal quantity for a 2 plus 1D conformal field theory. Okay, so let me just on that note mention what are the two, I would say, two very big usefulnesses or whatever. I don't know what's the right English here, but uses of entanglement. One is generating interesting universal invariants to characterize a phase, to understand what are universal features. Other is constraining phase diagrams. Doesn't sound like a surprising thing. How do you constrain phase diagram using entanglement? So that's the relation to so-called, so there are these C theorems in general dimensions, which tell you that there are these numbers which characterize a conformal field theory. And if one conformal field theory becomes unstable to something else, then suppose this is your CFT1, CFT2. CFT2 could be trivial. It could be fully gapped system, but that's still a CFT. There's nothing there. So then this number, for example, C, will never increase under this RG flow. So this by arrow, I mean you sit here in the CFT, you turn on some coupling, which is a relevant coupling under RG, and it just happens that there's a theorem which shows this. So the generalization of these theorems to higher dimensions were not known until, I would say, 14 years ago, 13 years ago. And they were found using thinking in terms of entanglement entropy for this number F. So that if you go to 2 plus 1D CFT, Then you have F1 here, F2 here. And again, there's a similar inequality. F1 is bigger than F2. So this is a famous result, which so all its major contributions came from high energy physics. This work is by Cassini and Huerta, but also built. I mean, this conjecture is related to some other works in high energy, which came from ADS-CFT. Okay, so at least it's. I hope at least I've convinced you it's a useful quantity to think about this notion of entanglement. Any questions there? Yes. Oh, so sorry, this hash here. Oh, sorry, I should have said. So this is a non-universal coefficient. But whenever I draw something like this, sorry, is my notation to mean something I don't care about, I draw it like that. LA is a subsystem size. So the leading part of entanglement scales with system size. There is a subleading constant which is independent of LA. So think about a Taylor series expansion in 1 over L. Right. So this is a leading term, this is a constant term, then there is a 1 over LA and so on. Yeah, so this is I'm always denoting the linear size of the system as LA. So in this case, the radius of the circle, thanks for clarifying. So the radius of this circle is let's say whatever, proportional to LA. So that's why this is called area law of. So that's a good point. Thanks for reminding. So this is called area law of entanglement. So if you go to more than one in 1 plus 1D, there is a violation. There is a log LA. But if you go to 2 plus 1D, its leading term is proportional to the boundary of the system. If you go to 3 plus 1D, it's again proportional to the boundary, which is LA square, and so on. And the intuition is that most of at least the short distance, there's a short distance part of entanglement, which comes from integrating out some kind of correlation between this region here and this region. Let's say this is A, this is B. So you're kind of patching up some correlations locally, which give you this leading term. But that's somehow not enough to account for all correlations. There exist some long distance correlations, long range entanglement, which is captured by this F. Same thing, this gamma. If I look at this expression for topological entanglement entropy, this is again the area law. This is again non-universal and should be again thought of as kind of adding up contributions close to the boundary, some very local effect. And this gamma cannot be obtained by some local patching. And we will go over that argument soon, once more. Not once more, but when I come to mixed entanglement, we will revisit that point. Yes. So this number can change. So it doesn't tell you what full SA does. For example, this number can also change dramatically, right? But that's not universal. So this statement is only about the subleading term, that the subleading term decreases under RG. But it does not tell you what the leading term does. In fact, that's a very good point, and it will come back again. This question about total entanglement versus universal part of entanglement. So that's why, in fact, I made even a kind of a problem on that. For example, at least in if you look at any quantum information literature, like people in 1990s when they were thinking about few qubit system, not many body systems, often they put constraints on entanglement based on what they call LOCC. Has this acronym been introduced so far? I think no. Okay. That means local operations and classical communication. So you have two parties, A and B. So let me just mention it right now. So you have two parties, A and B. They can talk with each other over classical phone, like your cell phone, and they can do local quantum operations. For example, they can apply. So imagine just the simplest example. I have 1 qubit. You have 1 qubit. On my qubit, I can apply any unitary. I can measure it also, but I can't apply any unitary on your qubit. But I can call you and tell you which unitary you should apply or something like. I mean, I can do classical communication and so that's called LOCC. And the reason I'm mentioning it right now is because there are constraints on entanglement from LOCC. For example, you might have heard under LOCC operations, entanglement always decreases or never increases, let's say, right? So that sounds like this. But there's a huge difference between these two things, because when we talk about LOCC, we are talking about full entanglement, SA itself, not some universal part of entanglement. So that's why there's a bit of a tension between the way condensed matter people think about entanglement and the way quantum information will think about entanglement. Because, for example, the whole reason LOCC was a useful idea was because it gives somehow a natural ordering of states. States which have more entanglement can be converted to states which have less entanglement, because entanglement never increases in the LOCC. So that was a usefulness. So you might be tempted to call states which are more entanglement as more entangled, right? That sounds tautology, but it's not true in condensed matter. If you ask a condensed matter person, what is more entangled? Take some product state, like a like some completely trivial paramagnet, do some short distance entanglement, and compare it to some topologically ordered phase, like toric code. Most people will condensed matter will say toric code is more entangled than some almost product state. But I can convert an almost product state to a toric code using LOCC, because LOCC only cares about total entanglement. So that's, yeah. So I think there's some kind of one needs to perhaps find a refinement of LOCC, I think.
That's still an
No. If I do across, so let's say this is region A, this is region B, I can apply local gates which cut across A and B. So that's not LOCC. Anything which goes across is not LOCC, even if it's low. That's the whole point. In fact, yeah, that's great. So yeah, you have a question.
Can I just ask a question about? I have trouble distinguishing this alpha gamma finite size correction.
No, I'll come to that argument very soon to show that it cannot be a finite size correction. So there's a general argument. So we'll come to that. But coming back, let me finish that LOCC thought. So you might have, I mean, this is now kind of a, I don't know, part of a modern culture, right? Preparing interesting states using measurements, right? Everyone is talking about it because it is super cool, right? It's the fact that you can prepare highly entangled states using just measurements. That's pretty cool, right? You can, because most of the platforms have limited fidelity, so you can't do very deep circuits and so on. So it's a very practical thing, and a lot of stuff we will discuss in this mixed state will be also motivated from that. So now you might have heard of this specific protocol. Take a product state, let's say on a square lattice, and just measure all the stabilizers of the toric code. So just measure all the four product of four things, and you have prepared a toric code ground state. If you let's say post select on the right, it doesn't matter. Even if you don't post select anything, it's a highly entangled phase of matter, a highly entangled wave function. So how did you generate a highly entangled thing starting from something which has zero entanglement? Because what you did was not LOCC. So that's not okay. Homework. Think about why this was not LOCC. Maybe it was obvious from what I just mentioned. I mean, answer is basically there. So, all right. But but don't worry if you, I mean, some of my parenthetical comments, if you don't understand, you can ask me later, but what I'm writing on Blackboard, that's probably closer to what I want to say. Other stuff is just, okay, just to get you, I don't know, get thinking about things more deeply, but okay, so at least, okay, so now we have at least introduced this idea of entanglement being a useful thing for generating universal numbers, and also for constraining phase diagrams. Okay, so in fact, let me give one. Okay, let me just give one application of this, just to kind of show you how this could be useful. For example, let's say you have some experimentalist comes to you and they say that they have this system which seems to be somehow self-tuned to Kitaev honeycomb gapless phase, right? So you have Kitaev honeycomb model, hopefully you have heard of it, which has this gapless phase, which has Dirac, I mean, low energy theory, it looks like two Majorana cones coupled to some zero gauge field. And they, okay, now the experimentalists say, okay, now I apply a magnetic field and I get some topologically ordered phase, which has maybe the topological order corresponds to, let's say, some Fibonacci anyons or some crazy phase, right? Some topologically ordered phase. And you can just tell them this doesn't make sense because of this monotonicity, right? They could be that whatever they're finding is inconsistent with quantum mechanics. Like that's a strong statement, right? So that's the kind of stuff you can conclude sometimes just using just combination of some definitions and quantum entanglement. Okay, all right. So any other questions? Oh, yes.
In this regard, do you know in the many body context the relation between entanglement and the CHSH inequality?
Right. So sometimes, so the examples I'm more familiar with, the constraints of entanglement are stronger than Bell's inequality, Bell's-like inequalities. So there are cases where, at least in few qubit systems, that's where I'm more familiar with this analogs of Bell's inequalities. There are cases where a state is entangled. You can show that in a very precise way, but it doesn't violate any Bell inequality at least in the usual sense. So there always exists something else like entanglement witness, which can be related to, but the most, I would say, old-fashioned Bell inequalities are sometimes not violated, despite state being despite state being entangled. So, okay, so now, so far I'm not tell you why are we calling this entanglement to begin with, right? This is some object. So why should we? So it has some very nice properties to be called entanglement. So one very nice property of this is if I give you a state. So let me move there. Sorry, not maybe. Yeah, I think I will write in this sequence and then we will move up and then. So consider a state of the following form. So this is a product state, right? So how would you prepare this state? So person A or party A prepares phi A in their lab, and party B prepares phi B, right? That's it. This is a tensor product state. So there was really no talk between party and party B. So these are called these clearly have no entanglement. This is how notion of entanglement in fact should be thought about. I mean, so first to define what is not entangled, right? And you would like any good measure of entanglement should be 0 for such things. And then you can put few more conditions. Okay, there are few more conditions. For example, it decreases under local operations and classical communication and so on. So if you put just few such constraints there, I think 3 or 4 of them, you can look up your favorite quantum information book. But if you put those few conditions, you find that thing I wrote, trace rho A log rho A with a minus sign, is a unique function of density matrix of rho A, which should be called entanglement measure for pure states. So this is an entangled. So I will use the following 2 words interchangeably unentangled or separable. So this is a separable state, and you can just check that S of A is 0.
Does this depend on the basis?
No.
Yeah, I'm thinking if you start from the momentum form space, then you go to the real space. It looks like a state of difference.
Right. But you're not. Yeah. But if you do, if you do once you have done, first you have to define Hilbert space, right? Hilbert space. When I write down, for example, R versus K, that's that's not very precise way of thinking about things, right? You have to first. If you have some system in real space, once you have defined what its Hilbert space is, any change of basis is just a unitary transformation. Because of this trace here, trace is invariant under if you do U dagger rho A U, right? So if you write down rho A goes to some U dagger rho A U, it's invariant because of the trace. Yeah. So I think you have to be. So sometimes you might be thinking about, let's say there's a consider let's say even a single particle, let's say, and then you divide the space into left half and right half. Maybe it's a plane wave, it looks entangled, but in momentum space it looks like a product state or something like that. But that's not direct. There's a difference between direct product and direct sum, right? What you're thinking was more like direct sum. If you have a Hilbert space with a direct sum of two subspaces, then you can't talk. Then if you try to define some analog of entanglement, which is basically not very well defined anyway, but if you try to define it, then you may run into such kind of confusions, whether it's real space or momentum space. But if you find Hilbert space as a tensor product of two Hilbert spaces, then really there's no ambiguity. It's just a unique. It's yeah. All right, great. Please continue. Actually, I was supposed to repeat questions. I have not done it even once. I'm sorry. All right. So, okay. So, everyone comfortable at least with the notion of entanglement? It's something. Okay. How many of you actually have heard of entanglement before? That I should have asked. Okay. This is good. It's not. It sounds almost. But if you haven't, they are good review articles. I think one of the most useful review articles, I would say, for introductory purposes of the kind, for mixed state entanglement at the very least, is by Horodaces. Like there are 4 of them, right? You probably know there's. I think there's one father and 3 sons, and you can write it as a tensor product of 4 Horodaces if you like. All right, so there's a review of modern physics. I actually find it very useful. There's only one review of modern physics by these guys, and okay, so where are we? So this is some uses of entanglement for pure states. So now let me maybe try to give a maybe even broader perspective on mixed state entanglement, or the kind of questions we want to ask. That's how I wanted to start. But okay, at least this is more like more like a refresher. So okay, let me just start here. So it's at least we have defined for pure states, but is not entangled, right? So you should also and this is motivated from the fact that this state can be prepared without any quantum communication between party A and B, right? So then you can ask, is there some generalization of this idea to mixed states? By mixed states, okay, what is mixed state versus pure state? Just to, okay, if pure state is just whenever you can write row as something like this, that's called pure state. If you cannot do it, that's called mixed state. So, okay, so this has the property row square is row. So trace of row square is trace of row, which is 1. That's called purity. So that's purity is 1. For a mixed state, that won't be true. Trace of row square will not be 1. So the most kind of a natural extension of this. So what is a mixed state? Mixed state is a ensemble. The right way to think about that is mixed state is just an ensemble of pure states. You're given, let's say, one pure state you prepare with some probability. So imagine like the following setup. They had parties A and B. They share a classical coin. Like they can toss a coin with maybe not just two sides, with multiple sides. Depending on what the outcome of that coin is, you prepared one such state, such an entangled state. That sounds not very hard thing to do. I mean, I'm sure people are already doing it, doing this experimentally all the time. So since the quantum part of this preparation is still easy, you have to just do local operations in A and local operations in B for quantum mechanically. Such states should be called unentangled mixed state. So that's a definition of a unentangled mixed state. So So PIs are some positive numbers. Think of them as probabilities. So, so this state can be easily prepared. By easily, I mean does not require any quantum talking between A and B. Okay, so far so good. Is this definition clear? Okay, so sorry, what I'm writing is incorrect. Sorry, yeah. Thank you. Yeah, so so this is also called separable states. So okay, so we would like to know what are the if a state is not like this, right? That's often we are interested in things which are not boring like this, right? This is kind of not interesting from entanglement perspective. Entanglement is 0. We want to understand when states do not take this form, how to characterize their universal properties. What is quantum about it, right? That's the kind of key question, because such states are now being prepared all the time in experiments, especially with combination of unitaries and measurements. Such things can be prepared, and the question is, how would you know it's interesting? What should you calculate? So that's where we need to think about mixed state entanglement measures. What are they? How are they kind of in different known contexts? I mean, I think the picture for the many body mixed state entanglement is still, I would say, is still very incomplete. We have some patchy understanding, but based on that, at least we see some aspects, and we will kind of try to go through some of them in these lectures. Yeah. So the most kind of perhaps the common mixed state that you have heard of in your physics education is a Gibbs state, e to the power minus beta h, right? With probability e to the power minus beta, some eigenenergy beta e, you prepared state labeled by, let's say, the symbol I, right? So that hopefully all of you have seen in your statistical mechanics course. Yes. No. I'm asking. No. Like for the pure state, right? We only talked. We wrote down the full state over a Hilbert space A tensor B. This we call an entangle. So I'm just taking that same logic to this. So when we talk about unentangled, we have to talk. We are asking if I'm calling something an entangle, I mean an entangle between these two parties A and B. So of course I have to then write down the rho. So that's a special example of this, right? So if you have just one term, suppose there is only one term, that's one example of what you mentioned is like rho A tensor rho B. This is like, sorry? Yeah, so this is same as that. So how do you see that? That's the, okay, sorry, I didn't first catch your question, sorry. Right. But then you can, choose a basis for, you can do an eigen basis for rho IA and rho IB and expand that, and it will again look like that after some massaging. So this is equivalent to this. Because I'm not putting any constraint on them being orthogonal. These are not necessarily orthogonal. Keep this in mind. Phi I can be anything. Phi IB are not orthogonal. So I can, if I just expand this in the eigenbasis of rho IA and rho IB, you can relabel things and write in this label I will be some collective label of this I. Yes.
I mean, that's the one known an entropy of that is non-zero,
right? Exactly. So
no,
right. Exactly. So I will yeah, exactly. So I will come to all of those things. I think this is still, yeah, you're kind of, it's good that you're asking these questions. And so if you look at trace of sorry, yes, yeah. That's my definition. Yeah. Ensemble of things which can be prepared separately in A and B without any. Yes.
Many different unravelings.
Exactly. So that's the perspective we are taking. As in fact, that's how I start my lecture notes. That so consider, for example, okay. Yeah, I think this will take. I think yeah. I think now I see the pace I'm supposed to go. I feel like I will probably go. I don't know. I feel like I was worried I did not prepare much. Now I'm less worried, but I'm worried that I will not get to cover anything. But it's good that you guys ask questions, right? It's just for example, let's say with probability half, you prepare, for example, what example did I give here? With probability half, let's say you prepare 0, 0. So 0, I mean, let's say up. I don't know, but do you like 0 to be up or down? I almost settled in my mind down. Okay. So with p equal to half, you prepare this, but you can also do so this is one mixed state. Consider another mixed state. With p equal to half, you will prepare 0, 0 plus 1, 1. So I will often drop the normalization factors just because it saves me time and you can always find it yourself. Right. So these are two different preparations, but these are same mixed states. So when we say mixed state, we don't distinguish between how we prepared it. We only care about the final outcome. So just to, yeah, that's why it was a very useful question, because yeah, I wanted to mention that point. So I will not distinguish, but preparation has implications, right? The first one can be this preparation of the mixed state we are talking about is can be done using starting from a product state, starting from separable. If you have only access to unentangled states and local operations, this can be done. You start from 0, 0, then you apply, let's say, XX, you get this. But this one, if you start from 0, 0, you can never get to this state. So this tells you that although you may be preparing it like this, but this state was still separable. You did not have to do this. You could have done much less. Okay, so that was one point. So now let's maybe try to give maybe a sense of what kind of questions one may want. Sorry, you had a question. Yes.
I missed why you cannot go from 0, 0 to 0, 0 plus 1, 1.
I'm saying with only local operations between A and B. So okay, this is my A, this is B. So because this has zero entanglement, and as I mentioned, under LOCC, entanglement can never increase. This has zero entanglement, this has non-zero entanglement, so you clearly cannot go from this to this.
So like control disease and things.
Yeah, yeah, exactly. So think about this. So you can do U4 overall, right? If you have 2 qubits, the most general thing you can do is like in group U4. But if you're only allowed access to A and B, then you're restricted to U2 times U2 subgroup of that. But control Z is not part of that, or control not.
Same thing as saying single qubit gate.
Single qubit, yeah, I guess so. Yeah, I mean,
Well, in this case,
yeah,
the other cases,
yeah,
N over 2.
exactly. Yeah, correctly. So all right. So so let me try to motivate some broad questions which are unique to mixed states, right? So the pure states somehow are sometimes easier to think about because there is nothing like a classical correlation in a pure state, really. I mean, everything is just quantum. There's no notion of some mixing or anything. But when you talk about a mixed state, there is this kind of a very tempting to ask about what is quantum, what is classical, right? So let's take one example. So just to set up the stage. Actually, is it a clock? Okay, there is a clock. Okay. Okay, let me make an assumption. Let me make the following assumption, that the classicalizing model we call classical. I think that's reasonable to say. I hope you will not protest against it, right? Anyone against it? Okay. So let me write down H as minus this schematically on some, let's just call it lattice, nearest neighbor. So this is the classicalizing model, right? So we call it classical just because of that reason. So if I plot it phase diagram as a function of temperature, there is a phase transition at some temperature, let's say Tc. So this is a classicalizing model. So it's very tempting to call this transition as a classical phase transition, right? I hope so far no protest. Okay, now let me modify it. Add a transverse field. The phase diagram is this. Okay, now first stay at 0 temperature. Right, this is T equal to 0. So the phase diagram, just to remind you, this is a ferromagnet phase. This is the paramagnet phase. Okay. Everyone familiar with this? If not, please ask me if any questions here. Don't feel you have to know. I mean, it's not like any questions. Okay. You can just, yeah. So in one limit, this term is dominating. In this limit, H is large, so it just everything points along x direction. It doesn't break any symmetry. So if temperature is 0, there is a phase transition here from paramagnet to paramagnet. Again, at least it's natural from most people will say that's a quantum phase transition, right? This is 0 to 0 temperature phase transition. That's like, in fact, the canonical example for example, in Subir's book, right? That's the chapter 1 of Subir's textbook, Subir's Sachdev textbook. So this is like I don't know, this is a quantum phase transition. So this is a quantum transition. At least you might say, okay, what's in a name? Okay, but it means something when we say something is quantum, right? Quantum mechanics is different from classical mechanics in many ways. So these names are important. So this is a quantum transition. This is a classical transition. So no one protested against these things. So what about this whole line? What would you call this? So again, I'm working in a this is a mixed state question, right? Because I'm working in thermal equilibrium. There's a notion of a temperature. So I'm really studying something like e to the power minus beta h. Great. It is so, but how does one make that precise, right? Why should we call it classical? What notion of, let's say, correlation are you using to say it is classical, right? That's the kind of question we want to ask. Yeah, so that's, I mean, I will agree with you from my perspective, but how does one see that more precisely, right? So this is one class of questions you can ask. You have some system in thermal equilibrium, you have some phase transition. Should we call it quantum or should we call it classical? So the one perspective, like the standard perspective, is that you can write down finite temperature correlation functions of any kind as you can map it to a slab where this is your spatial directions, this is all space, and this is your imaginary time. The slab thickness is beta. So when you go to 0 temperature, this really becomes an extra dimension when beta goes to infinity. Beta is 1/t. So that's why this thing is very tempting to call it I mean, it's not classical, it's some new universality class. This is all of this line is actually in the 2D universality, 2D Ising universality. And this one is 3D Ising. So that's why that's why it's very natural to guess this whole thing is classical. And because, so you can think of the system at finite temperature in this slab. So you can essentially like a 2D Ising model with some maybe a large on-site, large but finite number of degrees of freedom on-site, right? This is some, if you like, e to the power beta number of e to the power beta, some, again, I pulled this, my favorite symbol, e to the power beta number of spins per site. Beta is finite, so it looks like a 2D Ising model with maybe just some enhanced local, whatever, how many local degrees of freedom there, but who cares about how many of them are there as long as it's finite. Universality still can't change, right? Okay, maybe that's like the conventional point of view, but I will protest against this for the following reason. So we can go to consider, for example, 40 Tori code, right? So again, this may sound like suddenly out of blue, I'm pulling out some fancy model, but there similar situation arises if you take Tori code in 4 dimensions, 4 spatial dimensions, and then most people would agree that at finite temperature, there exists what is called quantum memory. You can use it as to store quantum information. You can use it as a quantum hard drive, 4D Tori code. Four space dimensions. I don't want to call it 4+1. Same thing, I will not call this 4+1. I mean, I will not call this 2+1 because this is finite, 2+1 at beta equal to infinity, but four spatial dimension. So you can use 4D Tori code and we will discuss that hopefully soon. So the 4D Tori code can be used as a way to build a quantum hard drive. You can store quantum information which is not decohered by thermal fluctuations. So it's very very natural to call that finite temperature phase as really a quantum phase of matter. So, and when you lose that physics because of thermal fluctuation, that's some high enough temperature, it's very natural to call that a quantum phase transition. So that's why at least it's a basic question to ask, but it's a general framework for quantum versus classical, which agrees with all the, like here it should agree. You should not like cook up something which completely changes like even things which you really understand well. I mean, but it should agree here with our intuition, but also agree with new scenarios. So that's one use of thinking about mixed state entanglement. So that's maybe okay. That's one motivation. So that's quantum versus classical transitions. That's okay. That's one question. Related question I already mentioned. If you have a topological order at non-zero temperature, like 4-iteratory code, how does one really make it precise? Relatedly, suppose I take 2-iteratory code at finite temperature, right? It has really no quantum coherence at non-zero temperature. They are point-like anyons. Actually, on that note, how many of you have heard of toric code? I think this is, okay. Yeah, I don't know whether, how much should I mean, I think it's just, otherwise I will never get to cover anything if I don't assume some stuff, right? Something has to be assumed. But if you have not heard of toric code, then you still have tonight, right? I mean, I will only touch it very briefly today, but I have my notes. You can look them up and read about it, right? I mean, there's some kind of, there has to be some common language to discuss things, right? So, yeah, that's the nature of my. I mean, the topic is mixed entanglement, and so. Okay, so if you take 2D toric code, if you look at finite temperature, again, thermal equilibrium, it has no really quantum coherence. It's all gone, and there's no phase transition at non-zero temperature. It just you can heat it up to infinite temperature. From zero, there's nothing in between. There's a crossover. But if you take 3D toric code, it has a phase transition at finite temperature, which is the 3D Ising gauge theory has a finite temperature phase transition. So you might say, aha, maybe now I have some finite temperature quantum effect. But as we will argue, based on, again, if you think about mixed entanglement, and you don't have to really, I mean, this answer could have been argued based on more, I would say, simpler perspectives also. But if you really want to generalize something, it's better to use a tool which is not specific to just one model. So that's why, that's another reason entanglement. So I should have mentioned that actually earlier on, that okay, I kind of hinted, when we use entanglement-based diagnostics in the context of at least pure states, it has been extremely useful precisely because once you have defined something properly, then even if, and maybe you can calculate it at some fixed point wave function where things are very easy, but when you move away from it, even then things work out as you suspected. Like that's what I meant by something universal. It's not just one point of the phase diagram where things make sense, but everywhere. So if you take 3D toric code, it has finite temperature classical memory. You can use it as a classical hard drive, but not as a quantum hard drive. And that again, if you want to see that, I would say most, let's say, in a very quantifiable way using entanglement or something like some kind of correlation which is quantized, that there again, mixed entanglement turns out to be extremely useful tool. So these are two kind of applications, one to quantum versus classical transitions, and then quantum versus classical topological order. Okay, these things are related, but here's a third. So let me make a list of things which I want to, at least I'm hoping to talk about, but we'll see how far we go. Am I supposed to erase this? Okay, yes. So. Sorry, I didn't catch. Sorry. So the 1D Ising model does not have a finite temperature phase transition. So that's why this question doesn't arise. But you can ask in D bigger than 1. But I'm saying whatever I mentioned here applies to all Ising models bigger than D equal to 1. Spatial D bigger than equal to 1. Yeah. So okay. So then quantum versus classical phase transitions. That's one question. Then finite temperature logical order. And then there's a very related question to this, which is if you don't have finite temperature topological order, consider, let's say, 2D Tori code, it doesn't mean it's useless. It only means that you can't store data which is protected from thermal decoherence without doing anything. But you can do what is called active error correction. So if you have not heard of it, but a rough picture just is this. Suppose you have not a thermal bath, but maybe much weaker bath. Let's say once in a while, someone sneezes, or maybe there's some, I don't know, some cosmic ray, which is actually a real thing. I mean, actual experiments, cosmic beams actually do cause decoherence. So once in a while, some photon comes and flips your qubit, which you did not want to be flipped. And you can model it by some language called cross operators and so on, but that's a technical part, doesn't matter right now. But you basically generate some local excitations in your system from time to time, right? So, and this is a probabilistic process. So again, if you want to think of this system as really as a quantum thing, mixed state is a very natural way to think about it. This whole thing, and the way to make sure your topological data is not corrupted is to keep an eye on it, keep measuring your whatever the so-called stabilizers to locate where are your excitations sitting, and try to annihilate them, roughly speaking. I mean, you have one excitation here, another here. They are connected by a string. Try to guess the right string, and just try to pair them up, and do your best. But if this process happens too often, then actually you fail to correct it. So this is an interesting phase transition called error threshold transition, which has been discussed. So such error threshold transitions are ubiquitous in quantum information, not only in Tori code, but for pretty much every code you can think of, certainly the stabilizer codes, you have these threshold transitions. And the way to kind of understand them naturally, again, is in terms of mixed states. And I think Ehud will also talk about it. But again, their mixed state measures have been useful. So this is error threshold transitions. All right. So these are three, somewhat related things. So what about something completely different, right? So the one thing which many of us are interested in this summer school are new phases of matter in quantum dynamics, right? Non-equilibrium states of matter and so on. So we want to characterize how, for example, thermalization does not, fails to occur in some system. You heard beautiful lectures from Professor Hughes recently, and on many-wide localization. I mean, I didn't get to listen all of it because I was, preparing my lectures, but I listened to some of them. They were, great. And at least so you know something about there are systems where thermalization does not occur, right? So there also, it turns out, and also there are things such as integrable systems. For example, Heisenberg chain, where thermalization really does not occur. So even in such contexts where some new phases of matter which are not just not chaotic in the normal sense of the word, their mixed state entanglement is again very useful. Just to tell you why, what's a big kind of picture is that suppose you have, so I think all of you have heard about by now eigenstate thermalization. Is that fair to say? Okay, good. So let's say you have some system. The idea of eigenstate thermalization is that the system acts as its own bath. So the idea, let's say, look at some region A, some region B. If B is sufficiently large, then it acts as a good heat bath for A. But if B is very tiny, obviously it cannot act as a bath for A, because there's not just enough stuff to act as a bath. And this can be seen by plotting, for example, entanglement between A and B as a function of subsystem size. Let's say VA over total volume. So total volume is V over V is VA plus VB. So you can plot. So you take, let's say, your pure state, let's say pure eigenstates of some cavity Hamiltonian, and plot SA. The same thing which we earlier introduced. It takes this form. So first it linearly increases with system size A, and then at about half here, when it reaches half, then it decreases. So this part, the rising part, is very natural for a thermal system, right? This part is just a usual statement that thermal entropy for a system at a non-zero temperature is extensive, because this is just when VB is bigger than VA, which is this region, then entanglement entropy of subsystem A behaves as if it was a thermal entropy of some system. And that's related to the fact that reduced density matrix for A essentially looks thermal. HA is the Hamiltonian for region A. Okay, but now if you go to this region, this is clearly not a thermal behavior. The larger the A is, the smaller its entropy. That's not thermal, right? That's very unusual. And that's precisely because B is not a good heat bath for A in this regime. So not a good bath. Mixed state also provides an interesting perspective on this. Let me actually get some water, sorry. This also relates to Leo's earlier question. When I given some mixed state rho, how should I think about trace rho log rho? As I said, we have to think about some mixed entanglement measure, and trace rho log rho is not a good measure, perhaps. But what is it then? So here's one idea. I think maybe I should draw. I need to keep this, but also draw a bigger picture. So let me erase that.
But your point is that SA will start going down if volume larger than that, let's say.
Yeah.
But rho A given by Gibbs would grow with volume.
Exactly. So rho A is not Gibbs in that regime. Yeah. So here's a mixed state perspective on the same thing. Let's divide the system into three regions. Let's say C, A, and B. Yeah, this is an important example. If you have not followed anything so far, it's fine. But I think this kind of I don't know, brings together a lot of ideas. So it's the same. So now consider again. Let's consider a chaotic system. So that a finite energy density eigenstates satisfy this eigenstate thermalization hypothesis. So they look, so they have that feature I mentioned there. So now let's try. So now let's look at row AB first. So let's look at row AB, which is trace over C. Let me denote the eigenstate as E. So now one can ask this. So this is a mixed. So let's ask few questions. But okay, what is the meaning of trace row AB log row AB? So what is this? And what's the entanglement between A and B? As a function of, let's say, size of C, let's say, or which is equivalently VAB over total volume. So I've not told you what I mean by this entanglement, right? That I've kept ambiguous, but that will turn out to be some mixed state measure, which we'll introduce later. But for now, let's just assume there exists some perhaps way to think about it. But let's first ask this question. First question. The meaning of this is what I've mentioned already. This is the entanglement between C and A union B, right? This is what it is. So that we drew there, right? That picture is already drew. So if I plot this, let me call this SAB is this. So if I plot SAB as a function of VAB over total, when I write down symbol like AB, I always mean A union B. So if I plot it like this, when VAB is small, C is acting as a good heat bath. So it looks like this. Now, so the basic idea is this: when C is highly entangled with, so in this regime, like in this growing regime, whatever, C is a good heat bath for A and B. So it means it's very, very entangled with A and B. Only then it can be good heat bath. And because of that, A and B cannot be highly entangled with each other. So this is the idea of entanglement monogamy. So entanglement, if A is highly entangled with, if C is highly entangled with A and B cannot be highly entangled with each other. And this can be captured using various inequalities like strong subadditivity. Is kind of it's not, there's a very defined entanglement monogamy using some very kind of very precise statement. Strong subadditivity of entanglement, which is an inequality which is satisfied by one entropy, is not exactly that statement, but it is close enough for this purpose. Okay, but there exists some inequality, let's just say, which tells you that this happens. What I just told you, that if C is highly entangled with A and B, then A and B cannot be entangled with each other. So if but to capture the entanglement between A and B, because so I have to think about now. First of all, I have to start from this state, row AB, and then ask what's the entanglement between A and B, right? So that's a mixed state question. So it turns out when you do that calculation using some mixed state measure, which we will introduce later, you get this picture. Then exactly same thing. Actually, I can plot it on the let me plot it on the same thing. So let's say this is SAB, and let me plot the entanglement between A and B as, let's say, let's say E A with B. Some I don't know, some notation I just cooked up here. But so it turns out it's basically zero in this regime. Yes. Maybe there. So SAB is the entanglement between AB and C. So let me just use the same notation for both. Let's say there is some entanglement between AB and C, and there is some entanglement between A and B, something like this. So there are not many colored chalk. Are there chalks like, I don't know, yellow or? Okay. Oh, great. Perfect. I think yellow is.
General state.
No. Okay, sorry. I think that's what I was mentioning there. So we are working with finite energy density states of a many-body system which satisfy urgency thermalization hypothesis, something which is chaotic Hamiltonian. So this I already drew here. It will turn out, if we do the calculation, which is actually partly a homework also, so it will be 0 here, and then it will become volume law, something like this. So this tells you precisely what you would expect based on monogamy of entanglement, that when C is highly entangled with A and B are not very entangled with each other. And when C is not a good heat bath, when C is not highly entangled with A and B, then A and B start becoming highly entangled with each other. So this kind of a this is a useful way to think about then thermalization in terms of mixed state entanglement. So if tomorrow, for example, you found a phase of matter where so if you really do this for some not fine-tuned system, like some completely random but more realistic system, this side will be area law. So this will be, here it's area law, and here it is volume law. So there's an area to volume law transition. By area law, I mean that EA with B scales with some linear length to the power d minus 1. Here it scales with linear length to the power d, which is L to the power d's volume, as a function of subsystem to system ratio. Sorry, that's the same axis. Sorry, VAB over V. So there's a sharp transition in a many-body system. Okay, and but tomorrow, suppose you have some new phase of matter, right? You just did numerics. You had perhaps no deep intuition, but you could do numerics, and then you found something where it is volume law even here in this regime, some mixed state entanglement measure, right? Then that's a signature of a breakdown of thermalization. You have found some completely new phenomena, some new phase of matter. So that's again, mixed state entanglement is a very useful thing to think about when we think about even thermalization. And there exists example like this, as you can guess. Yes. Yeah. So I'm assuming some spatial regions, some natural spatial bipartition. Yeah. So if you take a complete, like take the most canonical example of a chaotic system, is like a random state in the Hilbert space, which is very hard to prepare. It has some, I don't know, huge complexity, but okay, let's just take that state for which calculations are easy. Then it turns out, hey, it is exactly 0, irrespective of where A and B are, but it only depends on their size. So I assume, let's say both A and, let's say assume A volume of A is same as volume of B, and both scale with system size, only then this ratio is of course non-zero. Yes.
I was just wondering before about the size of C.
Right.
Bad is because as you slightly increase the size of C, the entanglement between the regions are getting smaller.
Yeah. So once more. Sorry, I think I.
I basically want to make sure I understand your definition of like your region C being a good or bad heat bath.
Right.
It has to do with when you're slightly changing the size of C, if your entanglement entropy in this case is going up or down.
I think that's one way to put it. Maybe the more easier way to put it, that when C is a good heat bath, entanglement between AB and C scales with volume of AB, very much like thermal entropy. So that's the meaning of a good bath. right? A bath is what makes the reduced density matrix for A union B thermal, a good bath. If it is, by thermal, I mean it looks like a Gibbs state. If it's a Gibbs state, it has volume law scaling. If it does not have volume law scaling, it cannot be a Gibbs state.
You didn't tell us how to compute the entanglement.
No. I think that's I will introduce some measure. I'm just motivating why we need to find good measure of entanglement for mixed states to begin with. But once you find them, they do behave like this.
How exactly do you calculate that EAFP? Is that something like conditional information?
No, it will turn out we will use entanglement negativity. There's some measure of entanglement. Yeah.
Page that you've drawn.
Right.
It's always the max that it can. Right? Like so everywhere on your x-axis, that's saying that C is acting like a good bath.
No, it's here. It is not good bath in this regime, right?
So this still the page curve is telling us the most. That's the most.
No. I define good heat bath. So the condition of good heat bath is that the reduced density matrix for A union B looks thermal. It does not here in this regime. Because if it was just E2 minus beta H, it will be if it looks thermal, it will keep going up. So this is what even in the context of black holes, if you recall the Hawking versus the usual, that's the whole point, that if it really was thermal, it would look like this. Yeah, you know what I'm saying. Yeah. Yes.
Expectations. So usual thermodynamics, I would expect, like I have a subsystem which is of some size, but the rest of the system is giant in comparison. So I'm usually
Right.
VAB over V to
Right.
be tiny, which is all fine.
Exactly. Then you are here.
Why is it such a so you're looking at VAB over V greater than half in this case? Why would you expect thermal anything?
I was not expecting, but the surprising part was even when VAB over V was not 0, even then in this regime it looked fairly thermal, right? So that was already surprising. For so let's take some chaotic Hamiltonian Ising chain with some Z and X. Even there, our current understanding based on ETH is that von Neumann entropy is perfectly linear up till this point. So this is the fact. Yeah. I mean, fact or not, okay, it has been checked in various ways, and there's a lot of conjectures along the way, but it's reasonably believed now. Yeah. Yeah, that's a good question. That if you just do a kind of more, I would say, conservative calculation, right? You assume VAB over V goes to 0, but I'm saying but for this specific quantity, it doesn't matter up to half. Yeah. So that's what I was saying. So in that case, the slope here is the thermal entropy density, but it is still perfectly linear. No, it's the thermal entropy density times volume of region. So that's the maximum it can in that temperature. So there's a general question, right? If I give you some energy of a system, what's the maximum entropy it can? What is the maximum entanglement entropy? It's this. So it's a maximal given that energy constraint. I think, yeah. Go ahead, yeah.
So you're is EAB should be 0 like even if it is slope.
Sorry, you're talking about the yellow curve or the white curve?
If the white curve has like a slope less than 1, still like to expect the EAB to be 0.
Area law, as I said. Not 0, but small, not volume law. It's I mean, if you divide it by total volume, it will go to 0 if you want to normalize things like that.
I may have missed it. Something already asked it, but for discontiguous regions in curve.
Sorry?
If you have discontiguous.
Yeah, it doesn't seem to matter numerically at least. Yeah. It's crazy. It's 3:30. I think, yeah, this was like a 2 or 3 paragraphs in my Okay, but yeah, I don't know. We'll figure out a way to pick topics. But I think this was supposed to be. I mean, this was supposed to be like the at least we still have 4 minutes. I think 3 minutes. Sorry. Yeah. So let me mention a few. So this was the 3 big applications. Let's see what is the other. Okay. Yeah. Now I can mention other things in sort of. Let me just mention in let me write. I was making some table here. So that this is the application is thermalization and or lack of thermalization. And let me mention one more, 2 or 3 more applications. They're related to it, roughly speaking. But one is interesting non-equilibrium steady states, right? If you have some open quantum system, which is not thermal now, like you have all kind of stuff like, I mean, I know you're doing some measurements, you're doing unitary operators, some combination. You can have some non-equilibrium things. So non-equilibrium things can be of many different ways you can do it. One is the idea of looking at steady states of some Lindblad equation, right? You can evolve something with some thing, and then you can get to some non-equilibrium state. There you can have some, if you want to characterize that non-equilibrium steady state, you have to, again, because it's an open quantum system, you have to ask about mixed state entanglement. So those are like characterizing non-equilibrium open quantum systems. So that's again, you have to understand, if you really want to think about, I don't know, some universal features, it's very reasonable to start thinking about mixed state entanglement. Relatedly, sometimes maybe you're not interested in some long time evolution, but even short depth channels, right? The kind of stuff recently several of you have been thinking about in the audience, right? So you have some initial state, and then you do maybe some mixture of measurements and unitary, and with some probabilities, you do those protocols, and then you get some mixed state. So even non-thermal states in short depth, non-thermal short depth mixed states. So these things are sort of related, but I think it's good to write down. So if you want to understand, again, I would say entanglement is a useful perspective often. And what else? Okay, let me make sure my. And then there's a very recent development. I mean, okay, some of you who are more, I don't know, more towards condensed matter, you might have heard of non-perturbative constraints from, for example, anomalies, right? And so if these words not mean much to you, that's fine. But okay, it's at least some of you probably think about these things at 4 in the morning, right? So this is like things like Lieb-Schultz matrix constraints and so on, right? So then there's, for example, there's one very, I just want to highlight one, I don't know, recent interesting work. This is work by Shinshiryu and collaborators, where they, using some Lieb-Schultz matrix-like arguments, they put some constraints on the spectrum of the Lindblad equation, and that tells you how the system relaxes. It won't tell you maybe necessarily about the steady state, whether it's interesting or not. That's a more, I would say, harder question generally. But relaxation to steady state relies on what kind of gaps are there in your spectrum of the Lindblad equation, and you can put constraints on those using some non-perturbative arguments. So again, I think there's a lot to understand there in terms of this non-perturbative constraints on non-equilibrium dynamics, and this is one of the, I would say recent work. So this is just, let me mention it here, non-perturbative constraints on dynamics. You can also ask non-perturbative constraints on phase diagrams of non-equilibrium systems. Like I was talking about this C theorems here, there is thing here, F1, F2 business. So far, we haven't found anything like that in mixed states, because I think the most useful tool there has been for pure states, so-called strong relativity of entanglement. There's nothing like that for mixed states, as far as we know. So far, like maybe in special context there is something, but so that's still wide open. So there's a lot of conceptual reasons. So at least you got at least a rough idea what kind of questions one may ask. But also from more technical side, I think sometimes this field is so, I would say, less explored that even some very basic calculations have not been done using, let's say, field theory. So I don't know, sometimes it's just good to calculate things for the heck of it and then later understand what you did, right? So even those kind of things have not been done, which like bread and butter field theory kind of calculation. There are a lot of interesting questions one can ask there. So that's more like on the technical side. And also from numerical side, I would say not much has been explored. So so these are more like technical things, right? Numerics, field theory, and so on, but how you calculate something. So I think there's a lot to do even just there, even if you, okay, we're not interested in these specific questions, but there's a lot to do here. So anyway, so at least you got a sense of what we want to talk about. So what we'll do in next couple lectures is maybe pick some of these topics. Maybe I mentioned some of them, and maybe go a little bit in depth and introduce mixed state. So what I have not even done so far is how to characterize mixed state entanglement. So we'll do some simple examples of mixed state measures, and then try to apply them to many body contexts and pick some of these applications. So maybe we will have to be judicious in picking because, okay, there are just 2 lectures, and but that will be my plan. And try to please, look at all the lecture notes still need to be polished, but I think they have enough stuff at the level we are talking to for you to work through things, and kind of please do try all problems. They are at a level which can be solved, I think, but just by reading it. You probably don't have to even look at any review articles or anything. I think mostly self-contained, I mean, the way it's written, so it should be able to at least try them, several of them successfully. And then if you can't, ask me. Should we stop here, or what is the? But yeah, keep asking. I mean, I didn't. Okay, this was okay. I finished, but you can ask any questions now. And yeah.
The first part, when like this was the page here, I understand that monogamy of entanglement on the less than one, I guess we're moving like entanglement is this statement of like structure filter this space, but here you're like kind of framing something about chaotic systems, I guess.
Yeah, I'm just saying when AB is highly entangled with C, A and B are not highly entangled. That's all.
That's true when this is one. But
when this is one, what do you mean? What is one?
But when the scope is less than one, like there is a lot of space for the A and B to still like A is not really that much entangled with C. Right?
I mean, this is still volume law, right? This is the maximal it can be given the energy constraint. So I think in yeah, I don't know the answer, but the way I'm thinking is that as long as it is as entangled as it can be given the subspace we are working in, okay, that's how it works out, at least based on the calculation. So yeah. Uh-huh. I think I didn't quite catch the question. I'm not. This is EA with B is some mixed state entanglement measure. Uh-huh. For this one. I did not conclude. I'm saying, okay, that's first of all, that's a calculation. That's what you find. I'm not saying it always is the case. So there are cases where this is still volume law, and this is volume law also. I'm not saying it follows from it, but I'm saying in chaotic system, that's how it behaves. Yeah. Yes.
Earlier on, you talked about the fact that it's possible to find and make there's a plus 1, 1, there's a plus 1, 1, probably makes 0 or 1. You remind me what the point there was?
A point is when we talk of mixed state, we do not distinguish between how we prepare it.
So should that be seen as topology of density as the only thing that characterizes it?
Yeah, what I mean is that suppose what I want to say is, suppose I give you a mixed state and we want to know how non-trivial it is. We should think of all possible ways of preparing it. We should not get tied to just one way of preparing it. We should, for example, most mixed state measures are, when you think about them, for example, sometimes you have to optimize something, some quantity, over all possible ways to prepare a mixed state. So that already implicitly you're assuming that it doesn't matter how you prepare it. As long as you can prepare it at all, then it's the same mixed state. Yeah. I would not call preparation as a fine-grained information. It's not in the mixed. That information is not in the mixed. I mean, a mixed state is just a matrix, right? At the end of the day, whatever you get after averaging everything. How you got it, that's, I don't know, someone's personal life. I can't. I mean, it's not my. Yeah. It's not business. I mean, how do you pay it? It's just true. I mean, that's how we think about density matrices, right? It's an ensemble of things. When we write on rho as pi rho I, and there could be many ways to write the same density matrix. They're all on the same footing. Preparation matters. Yeah, but I'm saying that if you care about the end thing, then it is the only thing. Maybe if you cared about the end product, then it is the only thing. That's what I'm trying to say. I'm not trying to say that there could be constraints. That's something that there could be constraints on how you, and that goes into that, right? Defining all this LOCC business, whether what kind of operations are allowed and so on, and that's part of the whole thing. But I'm saying that if I want to define how entangled a mixed state is, I'm just given that mixed state. I'm not given anything else. You could be given something. I mean, then there could be something like that where you have to know. For example, I'm sympathetic to these kind of questions because, for example, here's one question, right? When I write down rho as pi, some rho I, some sum of various things, it probably matters how many terms are there, right? Because if you have to prepare some simple state many times, but if that many is too many, that still is hard, right? If this sum is infinitely large, what is the kind of the Shannon entropy of this probabilistic distribution? That can have implications, right? If I write it as say rho as pi rho I, where each of these rho I is short range entangled. So it seems like this is not very entangled. But if this sum runs over so many different, whatever. If the upper limit of this is huge compared to some other, consider some other state, which is, let's say rho prime is p prime I rho prime I, where maybe this is some, let's say 1 to let's say just 2, and this goes from let's say 1 to let's say million, something like this. If these rho I's are not very entangled, but these ones are highly entangled, let's say to do the best possible decomposition, and you find something like this. By the standard entanglement measures, we will call this is less entangled than this. But if you, practically speaking, if it turns out that the best you can do to write this one like this, involves such a large number here, you have to repeat that experiment 10 to the power 6 times. All the experiments were easy. These million experiments were easy. You have to do short depth circuit. But maybe, I don't know, maybe overall time matters, right? Complexity matters in that sense also. How many times you have to repeat the experiment? So these kind of questions are important. I don't think people have, at least I haven't seen this being taken into account. So I agree with these kind of perspective. What I would like to say is that when I think about how complex a mixed state is, then I think standard measures would call this is more complex because it requires deeper circuits, each individual component. Yeah. I don't know whether I'm answering the question. Yeah, but I agree these questions can be asked of that kind, but whether these two things, which is maybe by some measure, this is, you would say, is harder, but
But is there an operational meaning to the entanglement in the sense that how many del pairs can you distill? And if you're given just the density matrix, regardless of how you prepared it, you will not be able to prepare any entangled resources regardless of how you prepared it. Is there an operational sense in which it is not entangled regardless of how you prepared it?
Like
in the example of probability half 0, 0, and 1, 1, or half.
Yeah. That's I'm saying that so a good mixed rate measure will tell you it is not entangled. That's the whole point. I'm saying that it doesn't matter how you prepared it, but if you find a correct mixed rate measure, it will have operational meaning. For example, as you mentioned, how many pairs you can create out of this, or how many it takes to form it, either formation or the distillation. In both cases, it will be 0 if it's a separable state. So it has an implication for actual any other questions?
Thank you very much. And tomorrow we'll look forward to paragraph 4 and 5.
But I think we one good thing is we touched upon a lot of things which were supposed to come later, right? So I think it's not like we just did that. I mean, a lot of things that this was supposed to be in. Yeah, but okay.